Welcome to this explainer. Today, I'm going to be walking you through my proposal, a breakthrough that sits right at the intersection of advanced chemistry, artificial intelligence, and the future of electric vehicles. Let's be real, we are facing a critical juncture in EV manufacturing right now. Consumers absolutely demand extreme fast charging, but that demand is pushing our current thermal management systems to the absolute brink. The stakes literally couldn't be higher for the future of your EV fleets, so let's dive right into how this proposal is going to solve this problem entirely.
I want to hook right into the heart of the matter with a single number, 5 degrees Celsius. That is the absolute maximum safe cell-to-cell temperature variance within a high-performance lithium-ion battery pack. If we go beyond this variance during extreme fast charging, we risk severe localized degradation, shortened battery lifespans, and ultimately catastrophic thermal runaway. This 5-degree bottleneck is exactly what's crippling the industry's fast-charging timelines right now.
So here is our roadmap for today's explainer. We'll be covering 1. The EV thermal crisis. 2. Transforming Palm to advanced coolant. 3. The carbon chain trade-off. 4. AI-driven thermal performance mapping. 5. Algorithm accuracy and validation. And finally, 6. Executive ROI and future outlook.
Okay, Section 1. The EV thermal crisis. Think about the current industry standard for a second. Indirect cold plates. They rely on thermal interface materials and these really complex physical channels, which naturally creates massive thermal contact resistance. Honestly, they have essentially reached their physical limits. If you want to extract the massive amounts of heat generated by fast charging, we have to move to a different architecture entirely. Direct immersion cooling. By fully submerging the battery cells in a dielectric fluid, we completely eliminate that thermal contact resistance. It is, without a doubt, the only viable future for your high-performance battery packs.
But here is the massive elephant in the room. What exactly do we submerge these electrical components in? Current immersion fluids are enormous liabilities. Fluorinated fluids, sure, they have excellent thermal properties, but they are highly toxic forever chemicals with massive global warming potential and just exorbitant costs. Mineral oils, on the other hand, carry extreme flammability risks and have really poor oxidative stability. As manufacturers, you're essentially forced to choose between an environmental disaster and a major fire hazard. We desperately need a better fluid.
Which brings us to Section 2, Transforming Palm to Advanced Coolant. This is where my chemical solution comes into play. We are engineering a superior dielectric fluid straight from sustainable agriculture. Now, natural vegetable oils are great because they're biodegradable, but they have a fatal flaw, a beta-hydrogen atom on their glycerol backbone. Imagine that beta-hydrogen atom as a weak link in a chain. Under high heat, it snaps, the oil degrades, and it becomes completely useless. My synthesis strategy replaces that vulnerable backbone entirely with neopentoglycol, or NPG. NPG has a quaternary carbon center, meaning it is structurally locked in with absolutely no weak links. By making this exact switch, we eliminate thermal degradation, giving you a fluid that can easily handle the extreme heat of your EV battery packs.
So how do we actually pull this off? It's kind of like a high-tech recipe that transforms simple palm oil into an advanced fluid. First, we combine fractionated palm-based fatty acids with the NPG polyol in a very strict 2-to-1 ratio. Then comes the magic step, a base-catalyzed esterification process. We crank the heat up to anywhere between 150 and 220 degrees Celsius. And to drive that chemical reaction forward and make sure it doesn't reverse on us, we continuously extract the byproduct water and methanol using deep vacuum pressure. Finally, the newly minted diester is rigorously purified to meet your exact moisture and electrical specifications.
Moving on to Section 3, the carbon chain trade-off.
Now that we have a stable fluid, we hit a wall. Engineering the exact perfect variation of this fluid introduces a massive hurdle that has historically slowed down biocoolant R&D for years. We can alter the carbon chain length of the fatty acids, all the way from short C8 chains up to long C18 chains. But there's a vicious trade-off. If we use short chains, the fluid has low viscosity. It pumps easily and cools incredibly well. But the flashpoint drops, meaning weaker fire safety. If we use long C18 chains, we get an incredibly robust 300-degree flashpoint for ultimate safety, but the fluid gets thick, which severely penalizes the vehicle's hydraulic pumps.
You see, modifying that carbon chain length simultaneously shifts dynamic viscosity, density, specific heat, and thermal conductivity. All of these variables mathematically plug into what's called the Murray-Ceph number. Think of this number as the ultimate master score for how well a fluid transfers heat. Finding the absolute perfect carbon chain length to maximize this master score creates a totally unpredictable, multidimensional matrix. Doing this through empirical, trial-and-error lab testing, it's far too slow. And, let's be honest, it is incredibly expensive for your R&D budgets.
And that leads us to Section 4, AI-driven thermal performance mapping.
This is where we transition from traditional chemistry into the core innovation of my proposal. We are going to eliminate physical trial and error entirely using data science. Instead of synthesizing endless, expensive batches of coolant in a lab, I've developed a predictive modeling pipeline that instantly maps structural inputs like carbon chain length and operating temperature directly to thermal outputs. We collect a targeted set of experimental data, thoroughly clean and pre-process it so the AI can actually understand it, and carefully tune the hyperparameters. This gives us the exact data set needed to train predictive machine learning models. To map this crazy, highly nonlinear relationship between the fluid's molecular structure and its thermal conductivity, we tested out a few different machine learning architectures. Primarily, we contrasted multi-layer perceptron artificial neural networks, which use interconnected layers of nodes to approximate really complex functions, against ensemble learning methods, which essentially combine multiple decision trees to form a much more powerful, robust predictive model. Let's break down those ensemble methods for a second, because it brilliantly illustrates how we combat predictive errors. Take bagging, for instance, specifically the random forest algorithm. It builds multiple decision trees in parallel using random data samples and then averages them out. This reduces model variance and stops the AI from overfitting to one specific pattern. On the flip side, we have boosting, like XGBoost. This approach trains models sequentially. Each new model explicitly targets and corrects the exact errors of the previous one, which severely reduces overall model bias.
Section 5. Algorithm accuracy and validation.
Now, theories are great, but I know you need to see hard data proving that this AI framework is technologically viable. When you compare the mathematical error metrics across our tests, it's pretty eye-opening. Standard decision trees, they completely failed to capture the complex thermal physics, scoring terrible R-squared values. But as we move up to the ensemble-boosted trees, the Gaussian process regression, and finally the neural networks, the predictive accuracy absolutely skyrockets, and the root mean square error drops dramatically. And here is the winning metric, 0.964. That is the extraordinary R-squared test accuracy we achieved by using a tri-layered neural network to predict fluid properties based solely on structural inputs. Think about what this means. Your engineers can accurately forecast dynamic viscosity and thermal conductivity computationally without ever stepping foot inside a physical chemistry lab.
Finally, Section 6, Executive ROI and Future Outlook.
So what does this actually mean for your bottom line? Here is the ultimate executive takeaway. By adopting this AI-driven chemistry pipeline, you gain wildly accelerated fluid optimization. You completely eliminate the continuous, incredibly expensive loops of physical lab synthesis. You get perfectly tuned dielectric coolants that keep EV cells well below that critical 5-degree variance limit. And most importantly, this translates to massive reductions in your R&D overhead. It is hands down a financially superior alternative to traditional thermal management development. The long-term advantages are just as profound. Your fleet can pivot to utilizing sustainable, biodegradable palm feedstocks. That means achieving total regulatory independence from those toxic, heavily scrutinized fluorinated forever chemicals. Plus, because these AI models optimize the fluid to minimize viscosity, your vehicles expend way less battery power forcing thick fluids through cooling pumps. That directly results in improved driving range for the consumer. It's a win all around. As the source research emphasizes, quote, machine learning-assisted systems enable precise, predictive management, optimizing cooling efficiency, and prolonging battery lifespan, end quote. Look, this isn't just a minor incremental upgrade, it is a massive paradigm shift. Data-driven engineering is no longer an optional luxury for high-performance electric vehicles. It's an absolute necessity if you want to stay competitive. The chemistry is proven. The computational accuracy is there. And honestly, the financial justification is undeniable. The only question remaining for this panel is, will you back this data-driven revolution in EV manufacturing? Thank you for joining me for this explainer today. I look forward to your partnership.